So as I was talking in the last lecture about macrostate and microstate, and macrostate basically is the same as the state that we think about in macroscopic thermodynamics. So if I'm specifying the state of a simple system, then in general, state of a simple system we specify, say, the internal energy of the system, then we can specify the temperature of the system, we can also specify the volume of the system, and so on, right? So in macrostate, basically this is exactly what we are also doing. Say for example, an isolated system, that's what we talked about, right? An isolated system of gas in equilibrium occupying a volume V, and however that macrostate has innumerable microstates, right? These microstates are basically, so this is the point, the microstates denotes the microscopic state of all particles in a system. This microstate basically, so for all particles we want to know the mass, then we want to know the velocities, Vx, Vy and Vz, that is the velocity components, and also the position x, y, z. So these will basically give me the microstate, right? And macrostate is basically the state that we specify, or state or condition of the system, correct? It's like a state or condition of the system. So for that I gave an example, and this example was that of a dice. So as you can see here, dice has this type of faces. So these are leveled like this. You can see there is 1 point here representing 1, and there are 4 points here representing 4, and 6 points here representing 6. So you have levels from 1 to 6. Now you roll a dice, you look at the top face, you look at the number on the top face, and you see that that is an outcome. Now if you roll both, if you roll 2 of these, and these are unbiased, and these are unbiased, then what you basically are looking at, you are rolling both the dice and you are seeing the outcome, and this outcome, now this outcome is what is going to provide the constraint, and this constraint is basically like, I have rolled the dice and there are two dice rolled, and we are getting, say for example, a sum which is, say, of these top face numbers. The top face numbers is, say, 6 and 2. So the sum is basically 8. So if I tell that, okay, I want all the outcomes to be such that I get an 8. I always get an 8. The sum of the two top face numbers give me 8. So that is exactly what I talked about, and that time, so this 8 is the state of this, 8 is the state that I am describing, or the constraint that I am describing, and that state of 8 is the macrostate. So this is the macrostate. So that sum of these two numbers have to be 8 is a macrostate, right? And for that macrostate to be achieved, you have several microstates like 2, 6, 6, 2, 5, 3, 3, 5 and 4, 4. So basically number of microstates here is 5, which gives you sum of 8. So this is one example. So if I tell, for example, I want a sum 7, that means my top face of one dice, so that is dice 1, and say this is dice 2, the top face should basically have a number, so here the number should be n1, and say here the number should be n2. n1 plus n2 has to be equal to 7. Now how many ways you can have n1 plus n2 equal to 7? You can have n1 plus n2 equal to 7 in these ways, like 1 and 6 gives 7, 2 and 5 gives 7, 3 plus 4 gives 7, 4 plus 3 again 7, and 5 and 2 7, and 6 plus 1 7. So you have total 6 microstates here, right? 1, 2, 3, 4, 5, 6, right? 6 microstates here, and the macrostate is 7, right? The number has to be 7. Again, if I tell, say, now look at an interesting thing. When I told the sum is 8, we got only 5 microstates. When we went for sum equal to 7, we got 6 microstates. Now think of sum 12. If I tell sum equal to 12, then basically the only combination that you can get is 6 and 6, so which basically gives you 1 microstate. So you are seeing now that different outcomes or different macrostates correspond to a different number of microstates. The number of microstates is not the same for all macrostates. Some macrostates have more microstates and some have very less. So if I look at this, I have done this. So there are basically, so what are the macrostates possible? So so when you have 2 dice rolled, you have 2 unbiased dice rolled, then you have, what are the macrostates possible? 2 is one macrostate that is possible. 3, 4, 5, 6, 7. So basically the sum is, now if it is 2, then the only macrostate that is possible is 1 and 1, right? It has to be 1 and 1. 3, you have 2 microstates possible. 4, you have 3 microstates possible, as you can see here. Then 5, you have 1, 4, 2, 3, 3, 2 and 4, 1. So you have 4 possible. 6, you have 1, 5, 2, 4, 3, 3, 4, 2 and 5, 1. So you have 5 microstates possible. But you look at 7, you have 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, 6, 1. Right? So there are 6 microstates possible for the macrostate of 7. For the macrostate of 8, you have 2, 6, 3, 5, 4, 4, 5, 1 and 6, 2. Again 5. Then again it starts reducing. For 9, it is 4. For 10 macrostate, the number of microstates possible is 3, as you can see here. 4, 6, 5, 5 and 6, 4. You cannot get any other combination, right, when you roll 2 dice. Now, for 11, it is like 5, 6 and 6, 5. And for 12, again, one single microstate. So, total number of microstates that are possible is 36, right? Total number of microstates that are possible is 36. 6 out of these 36 microstates correspond to the macrostate of 7. So, therefore, using that information, I can write the probability of finding a macrostate of 7 is basically given by probability of finding a macrostate of 7, or probability of finding microstates that will give rise to a macrostate of 7. So, this I can write is as P7 represents the probability of finding microstates corresponding to macrostate 7. Right? So similarly, I can calculate, for example, the probability of the microstate having, so what are the microstates that correspond to macrostate 2? That probability is 1 by 36. Okay, and for P12 it is still 1 by 36. However, for P7 it is 6 by 36, which is basically 1 by 6. So as you can see immediately from this chart, is that P7 is the most likely outcome because it has the highest number of microstates, right? It has the highest number of microstates. So it is the most probable, it's the most probable combination that we will see. That 7 is the most probable combination that we will see. However, 12 and 2 both are least probable combinations, right? Both have the same very low probability, 1 by 36. Now, this is for a very limited number of outcomes, right? We have very limited number of outcomes. Now, think of this. When my numbers become very large, then the probability of the most likely microstates or probability of finding the most likely macrostate increases to a very large number, right? It is like several orders of magnitude greater than the least likely ones, right? So this is something that we have to understand. Again, I just give you another example. Say for example, I have balls. So remember here, the outcomes that we are talking about, where we can basically distinguish, that is the thing. So you are looking at the distinguishable outcomes. So for example, this ideas of distinguishable is, again, I can show you that. So there are 4 distinct balls, A, B, C, D, right? They are marked as A, B, C and D. So there are 4 distinct balls and there are 2 distinct containers. So they are again labeled as 1 and 2. Now, how can we arrange these 4 balls in these 2 containers, right? How many ways can we arrange these 4 balls in these 2 containers? So for example, I can think of the number of microstates like this, like you have 1 and 2 and the distribution, right? How the balls will be distributed among this 1 and 2. So for example, I can have a configuration where all of A, B, C and D are in 1, but 2 has 0. Again, I can also have 3 in 1, so A, B, C and D, or B, C, D and A, B, D and C, A, C, D and B. So these are, again, this is like 3 balls in 1 and 1 ball in 2, right? Similarly, I can have 2 balls in each. So for example, C, D, A, B, C, D, then B, C, A, D, B, C, B, D, A, C and A, C, B, D, right? So all of these are possible. Again, you have 6. You see the number of microstates becomes 6. Now the macro state here is the state, right? The state is like 2 balls should be in the box number 1, and 2 balls should be in the box marked as 2, right? 2 balls should be in the box marked as 1, and 2 balls should be in the box marked with the number 2, right? And here this macro state is basically 3 in 1 and 1 in 2, and this is like the another macro. It corresponds to one macro state like 4 in 1 and 0 in 2, and we can also have the same thing like 0 in 1 and 4 in 2. That is again another state. So however, 2 in 1 and 2 in 2, this is like 2 in the container level 1 and 2 in the container level 2 is where the macro state that gives you the maximum number of microstates. So the maximum number of microstates correspond to the macro state. So maximum number of microstates correspond to the macro state 2 in 1 and 2 in 2, right? So this is the macro state. Please note that this is the macro state, right? 2 in 1 and 2 in 2. And what are the 6 possible microstates? We have C and D in 1 and A and B in 2, or A and B in 1 and C and D in 2, right? So basically, if you see one very interesting thing here, that there are totally 2 to the power 4 microstates here, because you have 2 containers or 2 placeholders. In each, I can have this, like you can have either of so for each ball you have only 2 containers, right? So basically you can go either here or here, right? There are 2 ways of putting A or B or C or D. Means I can put whatever be the number of distinct balls or distinct objects that I have 2 distinct placeholders. Now in these 2 distinct placeholders, there are only 2 ways I can put these balls. I can put A either in 1 or in 2. Similarly, I can put B either in 1 or in 2. It does not depend on whether I have put A in 1 or A in 2, right? So again, that's an independent event. So basically, if I think of that, it basically means that it is like 2. So A can be put in 2 ways in these 2 placeholders, B can be put in 2 ways, and C can be put in 2 ways, and D can be also put in 2 ways. So total, the number of total microstates is 16, and you can, if you add them, 1 plus 4 plus 6 plus 4 plus 1, you can see that it is 16. So 16 microstates are possible. What are the macrostates? 1. This is 1 microstate. This is 1 microstate. This is 1. This is 2. Third microstate. Fourth microstate and fifth microstate, right? Only 5 states are possible in this experiment, right? You have only 4 balls and 2 boxes. Again, the number is quite small. Now think of a larger number. How many? So basically, another important thing, I have used omega, the symbol omega, you can see here, to represent the number of microstates. For a given macrostate. So if I have a given macrostate, I am trying to say that, so omega defines the number of microstates for a given macrostate, right? So now think of this. I have 100 distinct balls. So again, 100 distinct balls or distinguishable balls, and I have two labeled boxes, right? Box 1 and box 2. So two boxes that are labeled. Now I have two placeholders and I have 100 distinct balls, and I am telling that, okay, what will be the number of microstates? It will be basically, if I go by the logic, previous logic, and which is correct logic, it goes to total number of microstates become equal to 2 to the power 100. So you see the number 2 to the power 100, which is approximately equal to 10 to the power 30, right? Now, what are the macrostates possible? Like 100 in, so there are many macrostates possible, right? 100 in 1, 0 in 2, 15 1, 15 2, 13 1, 17 2, something like that. So just let us consider 3 macrostates here. For example, 100 balls in 1 and 0 in 2, right? That is the macrostate A. And then 13 1 and 17 2, that is the macrostate B. 15 1 and 15 2, that is the macrostate C, right? Now, if I have to tell you how do you find the combination of 15 1 and 15 2, okay, so for example, if I want to tell you that, you tell me how do you find 50, so basically how many ways I can arrange these 100 balls so that 50 balls are in 1 and 50 balls are in 2, what will you do? So you have 100 balls, right? You have 100 balls, but you have 2 boxes. Now I am telling that in 100 balls in 2 boxes, you are basically looking at how to arrange 50 balls in 1 and 50 balls in 2, right? Or 30 balls in 1, 70 balls in 2. Can you tell me how do you calculate this probability? How do you calculate this number of 100 in 1 or 100? So how do you calculate this number of ways? So the number of ways, basically, if I can think of, how many balls are there? 100 balls are there, right? 100 balls are there. From 100, you are picking up only 2 balls. If that is so that is not what you are doing exactly. So can you tell me how do you do this? So I will tell you the way to do this, and then we'll come back to this problem, right? We'll come back to this problem, how to do this, 15 1 and 52. Please look at this problem again and try to find out, say for example, here it is A, B, C and D. So how did we find this number? How did we find this number 4? Okay, and how did we find this number 6? Now note this, that there are two boxes here, okay, and there are 4 balls, right? So you find out, and I'll go to, say for example, you see here I have given a formula. So I have given a formula, so I wanted to show you this formula, 4 factorial by 2 factorial, 2 factorial. Similarly, if I tell you the number of ways I can have 50 balls in 1 and 50 in 2, the formula is basically 100 factorial. So if I look at macrostate C, how many microstates will correspond to macrostate C? If I have to tell, so it will be like 100 factorial by 50 factorial, 50 factorial. You can try to find that out, and you can find out what's the value. But what I am trying to say is that that number comes out to 10 to the power 29. Now you see the now if you have 10 to the power 29 divided by 10 to the power 30, then basically you get the probability of finding C macrostate, and the probability of finding C macrostate is basically 0.1. So you have 10 to the power 29 microstates that correspond to macrostate C. Again, this is an approximate calculation. However, look at B, which is 100 factorial by 30. Now you will tell me how did you arrive at this formula. Just wait for a while. I'll show you how to count in such a case, right? In such a condition, how to count, right? Remember, the constraint is that total number of balls have to be equal to 100, right? It has to be 100, 70, 30, 100, 0, 50, 50, whatever be the combination. You cannot have a combination of 50, 49, right? That's the idea. So this is where the counting, the formula, this formula becomes very, very important, right? So basically, if you see, there are only 2 boxes, and you can have like you can think of like this corresponds to, by the way, a combination formula which is called 100C2. I'll come to that. So but what I want to show here, if I plot omega Okay, if I plot omega, so here I have plotted omega in the y-axis, and the most probable macro state. Now if you see, obviously the most probable one is this one, right? C is most probable one. According to, you can also consider many other macro states. You will see that the most probable one is the one where you are equally sharing the balls, 50 and 50. And you see that 0.1 is much larger than 0.00003 or 0, right? You can see the number of, if say for example the number of microstates is 1, then the probability is 10, so 1 e minus 30 or 10 to the power minus 30. So basically this is like, so it is like 10 to the power minus 30, which is very small. It's like approximately 0, right? So see that it's asymptotically 0, we can tell. So we can see that when the numbers increase, the number of species or number of particles increase, number of distinguishable particles increase, you can immediately see a very rapid change in the number of most probable macrostate, or the number of microstates corresponding to the most probable macrostate, right? Number of microstates corresponding to the most probable macrostate is that macrostate which will have the maximum number, omega max means which will have the maximum number of microstates. So the macrostate that corresponds to the maximum number of microstates is most likely, and it becomes more and more likely if the total number of particles that you are arranging becomes very large, right? So that's why you have a spike here. If you see here, we have given a spike here, right? There is a spike here because see, if you look at it, 10 to the power 29, it is even 4 orders larger than the B macrostate. B macrostate is 13.1 and 17.2, right? This is something, a take-home message. This is something that you have to very carefully understand and you can appreciate. Once you appreciate this idea, then you can understand how this formulation for entropy will be developed using this number of configurations. Remember, if you remember entropy, when we defined entropy, we told the maximum dissipation is what is favored. For example, entropy will change in such a way that, say for example, the entropy will change in such a way that it's always positive for the natural process or the irreversible process. Think of an irreversible process. Again, think of a pebble that I have thrown on a pond, and the pond has still water. Now as soon as I throw the pebble and the pebble impacts water, there are ripples all around it. And you can see a large number of ripples that will be formed, right, as the pebble hits the water surface. Now think of this. The pebble has to reverse, comes back to your hand, and all these waves, all these water ripples come together and become concentrated, and the pebble jumps back to your hand. Now that is a very unlikely process. But if you see the process where you have a lot of dissipation of energy, you have like a lot of ripples, is the most likely event, and that is where the entropy increases, right? And that entropy increase, as we have told, our entropy maximization gives you the equilibrium state, right? And it also gives you the natural direction of the process, right? So that's the idea. So let us look at this now with n particles and r energy levels, right? So you have like, if you think of a gas, for example, you have a lot of particles, these n0 particles, let us consider, and there are also several energy levels, right? Because, for example, if you think of quantum mechanics or something, quantum states, you tell that there are several energy levels. It's not an energy levels are not continuous, but there are discrete energy levels, and some of the atoms out of this n0 particles, some of the particles will occupy one energy level, some other will occupy another energy level, and so on, right? So basically, let us think of these energy levels like epsilon 1, epsilon 2 up to epsilon r. So there are r energy levels or states. R can be 2, R can be 100, R can be 1000, but these are discrete energy levels, right? This is not like a continuous energy variation, but discrete energy levels, and each of these discrete energy levels will contain some number of particles. Okay, so for example, n1 particles will go to epsilon 1, n2 particles will go to epsilon 2, and nr particles goes to epsilon r. Okay, so this arrangement of n1 particles going to epsilon 1, n2 to epsilon 2, and nr to epsilon r itself is a state, right? So Ni is the number of particles with energy epsilon I, and I goes from 1 to R. So basically, if I tell particle 1 in any of the R, now if I want to calculate the number of microstates, what I am telling, particle 1 can be in any of the R states, which is R ways. Particle 2 in any of the R states, again R ways. So in any of the R states, it's possible particle 2. So this R times R, which is R square ways. Again, particle 3 in any R state, so again R cube ways. So basically, if I tell particle n0 in any R way, so it becomes R to the power n0. Now think of this, instead of R equal to 2, if I consider R equal to 10, and if you have particles like 30, you see the number of microstates possible is 10 to the power 30. The number of microstates increase more than, it's very, very fast. The increase is very fast. It is more than exponential. So you can see, as soon as the number of particles becomes large, number of energy levels become large, right? The more the energy levels, the more is the dispersion or dissipation of the energy, right? Dissipation of energy is more when you have more possibilities or more distribution, means a wider distribution of energy. But what we are considering, these energy levels are discrete, right? So the energy levels correspond to boxes, right? So you had 2 boxes previously, now you have R boxes. R can vary from 2 to, it can be 1, it can be 2, it can be 100, right? And in general, in these large systems of large number of particles, there can also be quite a large number of energy states. So remember, when we talk about large number of particles, that's why it is called statistical mechanics. Because we are looking at thermodynamics of these systems with a massive number of particles. So we have to find out how to calculate and how to understand these quantities that we derive from this description of particles, large number of particles, and this large number of energy levels, and how to look at these configurations and how to interpret. So let us go ahead. So for example, we can think of R equal to 10 to the power 100. R equal to 100. So 100 energy levels. So basically 100 energy levels. Now there are 100 energy levels, and let us think of 1 mole of atoms, which is like 10 to the power 23 atoms. So basically R to the power n0, that is possible number of microstates, is like 100 to the power 10 to the power 23. It's like enormous. It's so large that it's like infinite. So the number of microstates is huge. Now, how many microstates correspond to the macrostate? See, the macrostate that we defined is what? N1 particles will occupy energy level epsilon 1, N2 particles will occupy energy level epsilon 2, and so on. So N3 particles epsilon 3, Nr particles epsilon R. Now, if I tell that this is my macrostate, this is one macrostate where we have N1 particles in epsilon 1, N2 in epsilon 2, and Nr in epsilon R. Now, in such a case, the number of microstates corresponding to this macrostate can be found by this formula, that omega equals to n0 factorial by n1 factorial, n2 factorial, nr factorial. So this is basically coming from combinatorics, right? This formula is coming from combinatorics. This is nothing but so we will see that. So omega equals to n0 factorial by n1 factorial, n2 factorial, nr factorial. You will see it comes from a product rule of the combinations. Okay, so I will go to that. Okay, so again, before I go to that, I want to show you the definition of this combination, right? Definition of C. So basically, if I have a set, okay, I have a set of n elements. I have set S containing n elements, right? I am going to a very basic combinatorics just to give you an introduction. Now, fix a k that is less than n elements to form a k element subset. So S is the large set of n elements. Out of that, we are fixing some k elements which are less than n to form a k element subset. So S, for example, is a set of 4 elements, A, B, C, and D. Now, 2 element subsets are AB is one subset, AC is one subset, AD is one subset, BC, BD, CD, right? But note that CD on DC, that means the order does not matter. C and C comma D or D comma C are the same. But number of distinct 2 element subsets are AB. AB and B are same. So AB, AC. they are not same, right? AB and AC are distinct. So AB, AC, AD, BC, PD, CD, and so that means we do not care about the order at all. We do not care about the order at all, right? So how to select the subset of 2 elements from a set of 4 elements is given by this 4 factorial by 2 factorial 2 factorial, which is also written as 4. So we also write this formula as 4C2, and 4C2 is nothing but 4 factorial by 2 factorial and 4 minus 2 factorial. Okay, so basically, or we can call it like, so select R elements of sets from an n element set is given by C, and so n element set, right, and R elements of set, which is written as C n R or NCR, or C n comma R, which is given by n factorial by R factorial into n minus R factorial. Now you will tell me, okay, that is fine, but why you have so many factorials here, like n1 factorial, n2 factorial? So I will use some product rule with this CNR. So I will show you that. So total number of positions, say for example, so if you look at the problem that we had initially, total number of positions, the problem that we told that there are n positions or n available positions, and you have n1 elements of type 1, n2 elements of type 2, and nk elements of type k, and they have to be arranged on these n positions or n sites, and such that n1 plus n2 plus, right, so such that the sum of this, such that the sum of all these numbers, right, so you have n1 elements of type 1, n2 of type 2, these types are distinguishable, remember. So type 1 is distinct from type 2, is distinct from type k. Now what we are telling is all these elements that we have, we want to put them on n sites, such that n1 plus n2 plus dot 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 nk, that means n1 plus n2 sum up to nk. So basically n1, so if I have three elements, n1 is of type 1, n2 of type 3, type 2, and n3 of type 3, and you have total n sites, we are telling that n1 plus n2 plus n3 equal to n. So no site is vacant, and all of all these elements occupy the sites. Okay, so such that, that's why this constraint, this is called a constraint. The sum of n1 to nk of sum of all elements of different types is going to be equal to the number of sites, right? So now start with this. We start with n1 elements. We can start with any other, okay, but we start with n1 elements of type 1, and that can be arranged among n sites. So you have n sites, n is much larger than n1, so it is basically coming from this combination formula. So C n n1 ways, right, C n comma n1 ways, and n1 particles of type 1, if you use C n n1 ways, now you have n minus n1 sites remaining, and you are now trying to arrange particles of type 2. So C n minus 1 n1 comma n2, that is so now we are looking at n2 subset from the remaining the remaining elements of the set, which is n minus n2. Now again you have n3 particles. See, remember, as soon as n1 and n2 are arranged, now you have n minus n1 minus n2 only remaining. Now that is your set remaining, or that is your positions remaining. In that you want to arrange, okay, or you want to arrange this number of n3 particles. So if I have to do that, so this will be obviously this is wrong, this has to be n3, right? So we want to arrange n3 particles in the available n minus n1 minus n2 sites. How many ways to arrange them is given again by this combination formula, right? Now you go on, and then you have nk particles of type k. So you have, how do you do that? You have filled up to nk minus 1, right? You have filled up to nk minus 1, right? And you are now, the whatever sites are remaining, on that you want to arrange these nk particles, right? So basically look at this. This is like n minus n1 minus n2 minus up to nk minus 1, and you have nk particles remaining. This itself is nk, right? So there is this many number of ways. So total number of arrangements, if I do, that is the omega, is basically you can use a product rule like C n n1 and then n minus n1 n2, like that, up to n minus n1 minus n2 up to n k minus 1 nk, Now if you do that, you get this product rule, which is n factorial by n factorial, n1 factorial, n minus n1 factorial. Again, here there is an n minus n1 factorial, and here it is n2 factorial and n minus n1 minus n2 factorial. Now similarly, here you have n minus n1 up to nk minus 1 factorial, and then here also, so you have n minus n1 minus n2 minus up to nk. So basically, remember that this basically n itself is equal to n1 plus n2 plus nk up to nk sum. So that means this last one, so therefore n minus n1 minus n2 minus nk is going to be equal to 0, but 0 factorial equal to 1, right? So 0 factorial equal to 1. So now you see n minus n1 factorial cancels, right? N minus n1 factorial you can cancel with this one, right? The denominator and numerator. Similarly here and here. Similarly it means, so all of these will cancel. So you have n factorial remaining, n factorial will remain, and see n1 factorial will remain, n2 factorial remain, nk factorial will remain. All these other terms will basically get, means you can cross them. Say for example, this one and this one are common, right? So you can remove them, right? Because these are not 0, so it's not 0 by 0. So these are finite numbers. So finite numbers, if they're same numbers, so that will be equal to 1, right? So you can basically do that. So you can cancel them, and you will. So what you cannot cancel? You cannot cancel n factorial. You cannot cancel n1 factorial, n2 factorial up to nk factorial. So basically, since n is this and this is the constraint, and we had n sites available and all these elements were there, out of which n1 particles were of type 1, they were indistinguishable, right? These type 1 particles are indistinguishable among themselves. However, 1 is distinguishable from 2, 2 is distinguishable from 3. So you have this formula n factorial by this. Now exactly this is the formula that I have been using, whether it is 4C2, whether it is 100C50, or whether it is 100C70, right? So when we had this one, so for example this one, I told for macrostate C that the number of ways is 100 factorial by 50 factorial, 50 factorial. So right, and here we told it is like n0 factorial by n1 factorial, n2 factorial up to nr factorial, right? So that's the formula that we also derive, okay, just by using a product rule. So now come to the probability. Let us come to the probability. So you have now we have come to n0 particles are available states, and the macro state that we are corresponding is like n1, n2 up to nr, and the sum of these is equal to n0. Then we know the number of, so this is basically omega is nothing but the number of microstates. So it is coming from n0 factorial because n0 particles were there and n0 sites are also there. Let us assume that so no, n0 particles are there. In this case n0 particles are there, but the number of sites available is r, right? R available states means R available energy states means there are R sites, and n0 particles, right? n0 particles have to be arranged among R sites. Now if that is so, the omega comes out to be n0 factorial by n1 factorial, n2 factorial up to nr factorial, right? But remember, this comes because n1, n2 up to nr, if I add them up, we get basically nothing but n0, right? So this is the number of microstates for the macrostate. So this is what exactly I want to tell. So number of, so this is, so omega, which is given by this, is the number of microstates for the macrostate correspond to this, right? This. So let us call this macrostate J. Now if that is a macrostate J, the probability of finding this macrostate J is like probability of finding a state where n1 particles occupy R means energy level epsilon 1, or means energy level 1, and n2 occupies energy level 2, right? So basically here we can like write like that, like here R equal to 1, here R equal to 2, like that, R equal to right? So N1 occupying R equal to 1, N2 occupying R equal to 2, Nk or Nr occupying R equal to 1. Now if that is so, you have omega and the number of microstates is R to the power N0, right? These are the number of available microstates, right? So omega by R to the power N0 is basically like N0 factorial by, this is a continued, please note that this is a continued product symbol. So I equal to 1 to R, Ni factorial. Are you seeing that? So N0 factorial by Ni factorial, right? So because omega is what? N0 factorial by N1 factorial, N2 factorial up to Nr factorial divided by R to the power N0, right? That is what is going to be giving me the probability of macrostate change. Okay, so again, if I just look at it, just to reprise all this, so you have 16 microstates, and you can see that you have like A to P, these are your different microstates, A to P are microstates. But if you look at the macrostates, then basically you are thinking of, because there are two boxes, right? There are two boxes, then you can tell that this is the macrostate, this is, as I told previously, this is a macrostate 1, right? Where you have 4 particles in 1 and 2, 0 in 2, or 3 in 1 and 1 in 2, 2 in 1 and 2 in 2. So these are the number of macrostates, and the macrostates have this type of configuration. 4, 0 means it corresponds to the microstate A, and there it corresponds to B, C, D, E. Then F to K corresponds to 2, 2. Then LMNO corresponds to 1, 3 macrostate, and 0, 4 corresponds to P. Now, if you see the probability of each, so if you see macrostate, the macrostate number 1, this macrostate, then you have 1 by 16, and the highest is when 2 by 2 and 2 are there, right? So only thing that you have to remember, as I told you from the spike, that when R is large and N0 is large, all of these are large, number of microstates correspond to the most likely macrostate determines the entropy of the system. Because that gives you the maximum number of energy levels, okay, over which the energy dissipation can take place. So number of energy levels available for dissipation have to be maximum, right? And that should correspond to, or that should determine the entropy of the system. So what determines the entropy of the system? The macrostate, the probability of finding the macrostate with the largest number of microstates, the macrostate that corresponds to the largest number of microstates is that macrostate that determines the this number of microstates will for that particular corresponding to that particular macrostate is what is going to determine the entropy of the system. So this omega max by Rn0, this probability is going to determine the entropy of the system, right? So again, I have drawn the same curve. So as you can see, omega max peaks here where it is the most likely macrostate. Most likely macrostate is the one where you have the maximum number of microstates, like omega is the number of microstates. So when you have omega max, then basically you pick up here and see the other ones, the probability of finding other ones are so low compared to this one. When you have number of particles, number of available sites, all are very large, right? So omega can vary over several orders of magnitude, but see, omega can vary over really several orders of magnitude, but S varies over only a few orders of magnitude, like 1 to 2 orders of magnitude. As a result, you will see that Boltzmann, when he hypothesized that how is it related to omega or the number of microstates, he used k is equal to kb ln omega. This is typical, because if you see, this is something that a genius like Boltzmann will always think of, because if you see, you have omega which can be very, very large, which can vary by over several orders of magnitude. We have seen that, right? 30-70 was 10 to the power 25, 50-50 was 10 to the power even with two available states, we had 50-50, which right? Even with two available states, we had 50-50 with 10 to the power 29, right? 10 to the power 29 macrostates, and 0, 100 or 100-0 had 1 microstate, right? If you have 100 particles in box 1 and 0 particles in box 2, then there is only one microstate corresponding to that. But if you have 50 particles in box 1 and 50 in box 2, it corresponded to 10 to the power 29, right? 10 to the power 29 out of 10 to the power 30 possible microstates. Now, if you see that, that is going to dominate, because 29 orders of magnitude, this is as large as that. But ACE in general, we have seen, right, we have looked at the problems, ACE in general does not vary to such like 29 orders. It varies over 1 to 2 orders of magnitude. Now if so the way to think of this, or relating omega to S, you require to take help of logarithm, because logarithm reduces the order of magnitude difference, right? If logarithm makes it smaller, like log of 2 to the power 5 is 5 log 2, correct? But if you think of 2 to the power 5, it's quite a large number. So this is the exact, that's why ACE, so Boltzmann thought ACE equals to KB ln omega. Another important point, this is something that you think about, is that since entropy is an extensive quantity, KB ln omega, right? But here what we are talking about, KB, remember this is Boltzmann's constant. Boltzmann's constant is always per mole, right? So this S here that we are talking about is per mole, right? Right, because KB is R by Na. So it's not, it is, so here S is like, like KB. If you think of KB is joules per atom Kelvin, while that is the KB unit. And if you look at R, it's like joules per mole Kelvin. So it is per mole, remember. Okay, so but it is per mole that you remember. But remember that since the magnitude, orders of magnitude are so different. Okay, but there is another important thing. When we have this extensive entropy, how do you define? So you think about it. How do you define the extensive? Because total entropy is extensive, right? Entropy per mole is not extensive. So here that what we are defining is like entropy per atom or entropy per mole, right? So if you want to define an extensive entropy in terms of the statistical configurations, how do you do that? Think about it. So Boltzmann hypothesis, as you can see, one of the most brilliant hypotheses that you have, it connects the atomistic description. One of the most important hypotheses that you can have, and that hypothesis basically connects the atomistic description of in terms of particles, right? Atomistic description of matter in terms of particles. Particles can be like atoms, it can be fermions, it can be bosons. So this atomistic description of particles is connected to the phenomenological thermodynamics that we study, right? We study the macroscopic phenomenological thermodynamics, where we have observed quantities or perceptible quantities, and these perceptible quantities are something that we can perceive, right? We can measure volume using the dimensions of a container, right? So basically we can measure volume of a system, we can measure temperature of a system. These are basically, and we have this macroscopic or phenomenological description of thermodynamics. But here this is done, Boltzmann connected that to the number of configurations of particles in large systems, right? So this is a very, very important hypothesis or law, S equals to K. Now what is consequence of Boltzmann's hypothesis? What are the consequences of Boltzmann's hypothesis? So you have n lattice sites. Na is the number of atoms of species A, Nb is the number of atoms of species B, then Na plus Nb equal to N. Let us assume that you have two species A and B, where Na is the number of atoms of species A and number of atoms of species B is Nb, and Na plus Nb equal to N. That means the number of the lattice size have to be occupied by either A or B. Then one can write Na equals to N minus Nb. Now omega is n factorial by Na factorial and B factorial, which is nothing but Cn and B, which is n factorial by Nb factorial n minus Nb factorial. Or we can write it as n factorial by Na factorial into n minus Na factorial because of this relation, right? This is the constraint. Now once you have done that, you have S, which is equal to KB ln omega, and KB ln n factorial by Na factorial and B factorial. And you know how the n factorial is. I have just given the formula, n times n minus 1 times n minus 2, and it continues up to 1, right? Now ln of n factorial, okay, this is called Starling's approximation. So ln means I will derive Starling's approximation. So ln of n factorial, if I just have to give the logarithm of the n factorial, what do I get? I get ln n plus ln n minus 1 plus ln 3, ln 2 and ln 1, right? Or basically I equal to 1 to n ln I, right? Now look at this, I equal to 1 to n ln n, the summation can also be written in a continuous way by using an integral. So basically limits are from 1 to n and you have ln x dx. Now if you have ln x dx, you can do integration by parts. Okay, well, here I have done integration by parts. So integral of ln x dx, so ln x I have taken as the first function, right, and 1 as the second function. So ln x dx and this first function, so d ln x dx, and this entire thing have to be integrated over dx. So now you get x ln x minus dx integral, and the integral basically what are the limits, 1 and n, right? So this becomes x ln x minus x, or so basically this becomes n ln n minus n, right, because x ln x minus x is there. So this becomes n ln n minus n minus ln 1, which is 0, minus 1. So this becomes ln n minus n, and this is minus. So this is minus, right? So this is minus, and so this becomes plus, right? Or you can write this way first. First you write this, and minus 1, right? ln 1 minus 1, and which is equal to n ln n minus n plus 1, right? So that's what. So basically ln of n factorial is n ln n minus n plus 1. Remember that. That's what I have derived here. Now, so if n is very large, that means, say for example n tends to infinity, like 10 to the power 23, then ln n factorial is n ln n minus n, because this plus 1 can be ignored, right? N is so large that plus 1 can be ignored. So it approximately becomes n ln n minus n, right? Okay, because minus of n plus 1, you are adding 1, and that 1 is so insignificant compared to n that minus n plus 1 is nothing but minus n, right? You can remove this one. N is so large that this plus 1 does not make any difference. So ln n factorial equals to n ln n minus n is a famous approximation that is used by Stirling and James Stirling, and this approximation is something that we will use to find the number of arrangements. Okay, and also to find out the ln omega. So ln omega is what we have to find out, because S equals to kb ln omega, and as you have seen, we have used two species, A and B, and we have Na atoms of A and Nb atoms of B, and the total number of sites available is n, which is Na plus Nb. Now if you do this, you continue doing this algebra. So you have ln n factorial minus ln Na factorial minus ln Nb factorial. Now you continue doing this. So n ln n minus Na ln n plus Na, Nb ln Nb plus Nb. So if you do this, you have this term, and this term, and you have Na plus Nb minus n. Na plus Nb minus n is nothing but n minus n, which is 0. So you have n ln n minus Na ln Na minus Nb ln Nb. Now you take n common, so you get ln n minus Xa ln Na minus Xb ln Nb. Now you go further. So ln n, so you have Xa ln, what did I do? So this goes to 0, right? So this goes to 0. Now this guy goes to 0 because Na plus Nb equal to n, n minus n equal to 0. So you have this term, and this term, right? This is the term. Now I keep n constant, so I get ln n minus Xa ln Na minus Xb ln Nb. Now I can do, if you see, Xa is nothing but the mole fraction. Xa equals to n by Na. So if I do this, ln n minus Xa ln Na now I want to make it like this. I'm writing as minus of xa ln na right, and this will be minus ln of n. Now this I will write this ln of minus of ln of n. Now this can be written as, now this there is 1, so if you see xb equals to nb by n and xa plus xb, because we have only 2 species, equal to 1, right? So using that condition, if I put xa plus xb here, so this becomes, if only I am taking these 2 parts, so I have minus xa ln na, so I have taken n common, you can see, so xa ln na minus xa plus xb ln n. If I do that, now you can see the other part is also there. So if I do this, what I get immediately, so I did not just want to make it very clumsy, but you can immediately see, I don't want to make it clumsy. So if you see, this should show you, you have, so you got ln omega equals to n ln n minus, this is a little bit of algebraic manipulation, minus nb b. Now na plus nb, then moles of A and mole number of A plus mole number of B equal to n sides, right? That's the constraint. Or if I can define, if I divide both sides, so I get by n, so I get here 1 and here I get na by n, which is xa plus xb. This is the mole fractions add up to 1, right? Now I just take, now these are the things, so basically now I take minus n common, and then it becomes xa ln na minus ln n, and here this will become plus xb ln nb. Now instead of ln n, here you can add xa plus xb, because x plus xb equal to 1. Now using this identity, you can now write this as minus n, and you see xa ln n, there is a minus xa ln n. So basically if you see, this is xa ln na by n, and this will be plus xb ln nb by n. So this can be written as minus n xa ln xa plus xb ln, right? So we are right, we got minus n xa ln xa plus xb ln xb, right? So this is what I have derived. So minus n xa ln xa plus xb ln xb. Now s is kb ln omega. So now it is minus kb times n, right? Kb times n xa ln xa plus xb ln xb. Let n be the Avogadro number. If n is Avogadro number, then n times kb is nothing but r, which is the universal gas constant. So s comes out to be minus r xa ln xa plus xb ln xb. Now since xa and xb are less than, see, remember, when xa equal to 1, then ln 1 is 0, but ln 0 is undefined, ln xb is undefined, because, right, because xb becomes 0. So xa and xb have to be less, it has to be greater than 0 but less than 1. That means they have to be fractional. If they are fractional, then the logarithms are always negative, right? The logarithms are negative. If you have xa, which is fractional, which is less than 1, xb, which is fractional, which is less than 1, then there the logarithms will give you negative values, right? So negative values with a minus sign here, and there it will also be negative. So as a result, the total sum will be positive, right? S is always greater than greater than 0. Another thing, if you plot this expression, because see xb is nothing but, so you can write this, the same thing we can write as s equals to minus r. I can do it for any number of elements. I can write summation I equal to 1 to say whatever number of elements you give, say I equal to 1 to k, and then I can write xi ln, where k is the total number of different species, right? K is the different number of different species. So now if I plot this, say for binary also, if I plot this, you will see the curve. If you look at this, so remember, so I can take xa equals to, or xb equals to x, then xa equals to 1 minus x. Now if I plot it, then what I'll get is, and say this is xb, you will see something like and you'll see that at 0.5 means x equal to 0.5, s, you get s equals to s max. This is basically s equal to s, right? So this is something that becomes very, very interesting. And if you see that now this new alloys are coming, which are called high entropy alloys, right? You have seen this name called high entropy alloys. Many of you have encountered such names, where you basically mix a larger number of elements, like 5 elements, in equal proportion. Why equal proportion? Because as I told you, see, when it is 50-50, it has the maximum entropy. Similar maximum configurational entropy, right? Because we are looking at entropy here from the standpoint of configurations, how many microstates, like maximum number of microstates, that corresponds to that macrostate which is likely, and that macrostate is going to determine the entropy, right? So, and that is always going to be the distribution where you have equal number of different species, right? So this is called high entropy alloy concept. Now if you see, high entropy alloy generally contains like n, which is number of elements, so k, which is like k can be like a, k can be like a, b, c. These are like different atomic species, right? Different species, like from the periodic table and so on. And k can generally vary from 2. When I am talking about alloy, then it has to be greater than 1. So 2 you can go to like 10, 12. But generally we look at 5 component, 6 component alloys. And if you look at that, immediately you can see this minus r xi and xi. It just basically becomes, when it is equal proportion, so it becomes, say for example you have 5 elements, it becomes minus of r 1/5 ln 1/5. And you are doing it like 5 times, like you are summing it 5 times, so it becomes into 5. So this becomes equals to minus r ln 1/5, which is nothing but r ln 5. So you have like k, so it becomes r ln 5. So if you have k elements, so basically this becomes, when you have equal proportion, when you have like xa, say I have 5 elements equal to xb equals to xc xd equal to xc, and these are all have to be equal, right? So these have to be equal, and the sum is equal to 1, so each has to be equal to 0.2. Now in this case, the entropy S, or you can call it S conf, because there is also a vibrational entropy that is associated. So this is the configurational entropy, and that is basically the number. It is determined by the maximum number of the macrostate corresponding to maximum number of microstates, and then we use Boltzmann's hypothesis. What I get is this S conf equal to R ln 5. Now you see, when I have 5 elements, I get R ln 5, right? R ln 5, and R ln 5 corresponds to 1.6, whereas ln 2 corresponds to 0.69. So as I increase the number of elements, and if I take equiatomic composition, right, each species has equal proportion, then I maximize the entropy, and I also increase the value as I go up and up, means in terms of number of components. Like 2 gives me 0.69, while 5 gives me 0.6, 10 gives me 2.3. However, it is very unlikely to get a 10 component alloy. This is because that not only this entropy that is we will show later, that not only entropy being one of the criteria, there are also different criteria in terms of atomic sizes and electronegativity difference and stuff, right? So we'll discuss this later. So I will in the next. So basically, please note this very important idea that we could derive, right? We could derive and we could connect this atomistic description of matter with the macroscopic description. Okay, so in the next lecture, I will tell how from this atomistic description I can basically calculate useful quantities like, see, I have calculated S. Now if I can calculate U, right, we know already how to calculate U, but can we calculate CP, CV and stuff, right? And what is this ensemble and what is partition function? So I'll briefly describe all of these in the next lecture. So thank you for this. Thank you for listening to this. Thanks. And if you have any question, please note, if you have any question, please post them in some comment section so that I can basically answer these. Okay, I can basically answer these. I can upload a lecture to address some of your queries. Thank you so much.